Welcome back to the deep dive. Today, we are taking a fascinating journey, and I really mean that. We're descending the temperature scale from the relatively warm world of your kitchen,
All the way down.
all the way down to the quantum mechanical extremes near absolute zero. We've processed a really substantial stack of source material focused entirely on cold physics, and it's amazing how it connects the engineering of everyday life with these truly bizarre quantum realities.
It's a fundamental area of physics. And what's amazing to me is that the underlying principle, this manipulation of energy and entropy, it stays consistent.
Right.
But the mechanisms we have to use, they get more and more intricate and, frankly, just plain weird as the temperature drops.
Yeah.
We literally start with mechanical work, and we end up manipulating the nuclei of atoms.
Absolutely. And our source material was really designed to take us on that comprehensive journey. We're going to start with the refrigerator, something everyone has. Then we're going to descend through these huge industrial processes like gas liquefaction plants. And then finally, we plunge into the truly exotic world of the million microkelvin regime.
And our mission today is to be your guides through this extreme temperature gradient. We need to understand not just, the mechanics of cooling, but the surprising conservation laws that pop up like isenthalpic processes, and then the quantum tricks like magnetic alignment that let us steal heat where normal thermodynamics just gives up.
Okay, let's unpack this. The most basic starting point has to be just understanding how we even begin to generate low temperatures. What's the surprising physics that underlies, the simple appliance humming quietly in your kitchen? So we're going to start right there, where everyone interacts with cold physics daily. The refrigerator. When you really analyze how domestic cooling works, you find there are two main principles. The first one is the one we all know.
The standard compressor fridge. We call it the vapor compression refrigerator. And its core concept, really, is all about leveraging the massive amount of energy it takes for a phase change.
You mean from liquid to gas?
Specifically evaporation.
Yeah.
To make that happen, you need what's called a working gas, something that's really easy to compress and turn into a liquid.
And the history of those gases is a whole deep dive in itself.
Oh, it is. I mean, originally they were using things like ammonia, which is highly toxic.
Right.
And then later came the chlorofluorocarbons, the freons, which were, thermodynamically brilliant, but an environmental disaster because of what they did to the ozone layer.
So what do we use now?
Today, it's mostly much safer hydrocarbons, things like isobutane. But the key takeaway is that the cooling, the action itself, is all driven by that phase transition from liquid to gas.
And the entire operation is this continuous four-step cycle. I think it's useful to trace the energy flow here because a refrigerator is really just a heat pump, right? It's moving heat from somewhere cold to somewhere warm.
It's exactly against its natural tendency. So we start with step one, compression. It's an adiabatic compression.
Okay, what does that mean?
The mechanical compressor, it forcefully squeezes the low-pressure gas into a much, much smaller volume. The pressure goes way up. And when you do that kind of work on a gas so quickly, and that's what adiabatic means, so fast that no heat can escape during the compression.
All that mechanical work has to go somewhere.
It translates instantly into internal energy, into heat. The gas gets intensely hot.
So now you've got this gas that is both hot and under high pressure. That heat needs to be dealt with.
Right. This brings in the ambient environment in step two, condensation.
The coils on the back of the fridge.
Exactly. The hot, high-pressure gas flows through those coils, the condenser, and it just radiates that heat out into your kitchen. As it cools down, while it's still under all that pressure, the gas turns back into a liquid.
Got it. So it has successfully dumped the heat that the compressor generated, and now it's ready to go inside the cold part of the system. It's a liquid under high pressure, but it's much cooler now.
Yep. So we've dumped the heat outside. Now we need to actually make things cold inside the box. And this requires a really rapid depressurization. That's step three, expansion.
Okay, how do you do that?
The high-pressure liquid refrigerant is forced through a tiny, tiny restriction. It could be a nozzle or what's called a throttling capillary tube, right as it enters the coils inside the fridge.
And the pressure just plummets.
Instantly and drastically. And this sudden drop in pressure lowers the liquid's boiling point, which sets it up for the most important part of the whole cycle.
Which is step four, evaporation, the actual cooling.
Right, because the liquid's boiling point is now way below the temperature inside the fridge. It instantly boils or evaporates inside those coils.
And here's the crucial physics point. Boiling takes a huge amount of energy, latent energy. It's called the heat of vaporization.
And this is the genius of the system. That energy The energy required to fuel the phase change from liquid back to a gas, it has to be pulled from somewhere.
It pulls it from the immediate surroundings.
From the interior walls of the fridge, the air, the carton of milk, everything inside. By consuming that internal heat to complete its phase change, the liquid turns back into a low-pressure gas, and the inside of the fridge gets cold.
And then the compressor just sucks up that cold, low-pressure gas and starts the whole thing over again.
Endlessly. It's a continuous heat extraction process.
It's a really efficient system. But what about the refrigerators that don't have a compressor? The ones that are totally silent?
Ah, yes. The clever alternative. The absorption refrigerator.
You see these in, like, hotel minibars?
Hotel minibars, RVs, camping mobiles running on a gas flame. Anywhere that noise is a problem, or you don't have reliable electricity, they achieve the exact same cooling effect.
Evaporation.
Evaporation, yes. But they replace that noisy mechanical compressor with a really elegant chemical process.
And our sources say the trick here is all about the high solubility of ammonia in water.
That's it, exactly. Instead of an electric motor doing mechanical work, the pressure difference is created with heat and chemistry. You start with a solution of ammonia just dissolved in water.
Okay.
That solution is then heated. It could be a tiny gas flame or just an electrical heating element.
So the sheet is the energy input instead of the mechanical work of the compressor.
Precisely. And this heat input, it drives the ammonia gas out of the water solution. This rapid expulsion jacks up the pressure of the pure ammonia gas, which then causes it to liquefy in the condenser, just like in the other fridge.
And from there, the cooling part is identical. It goes through a throttle, evaporates, and makes the inside cold.
Identical.
But wait, if there's no motor, how does the low-pressure ammonia gas get repressurized? How does the cycle start over?
This is the elegant part of the lip. After the ammonia has evaporated and done its cooling job, it flows to a different section called the absorber. And waiting there is the water that was separated out earlier, which has since cooled down. And water has an extreme chemical affinity for ammonia. It just reabsorbs, or you could say it swallows, the low-pressure ammonia gas really, really efficiently.
Ah, so that absorption process is what creates the pressure difference.
It lowers the pressure in the evaporator section and raises it in the condenser section, but it does it chemically. It completes the cycle silently and continuously.
So the core insight is that one fridge is driven by mechanical work, the other is driven by heat input. You can run it off a candle flame, theoretically.
You can. And you get the same result. It really highlights a theme you see over and over in cryogenics, finding these clever physical arrangements to get the phase changes you need without just relying on brute force.
Okay, so now we have to move beyond kitchen appliances. We're entering the world of true cryogenics, where the goal isn't just to chill food, it's to liquefy gases like air or even helium.
Right.
And to do that, we have to shift our thinking. We're moving from leveraging a big phase change like evaporation to leveraging the much more subtle forces that exist between the molecules themselves.
We enter the realm of the Joule-Thomson effect, or the JT effect.
Sounds important.
It is. The JT effect is the fundamental physical mechanism that really started the industrial age of gas liquefaction. It's the difference between chilling a can of soda and getting liquid oxygen for rocket fuel.
So let's start with the physical setup. The term our sources use is isenthalpic expansion.
That's the one. The setup is actually very simple, but the physics is a little subtle. You take a real gas and you force it through a restriction.
Like what?
It could be a fine valve, a porous plug of cotton, a tiny nozzle, we just call it a throttle, and the gas goes from a very high pressure P1 to a much lower pressure P2.
And critically, the whole thing is perfectly insulated.
Perfectly insulated. No heat can get in or out from the outside world.
Now, you stressed before that this is not the same as classical adiabatic expansion. Why do we need this new term, isenthalpic?
Well, because when we usually think of adiabatic expansion, we picture a gas pushing a piston, doing external mechanical work.
Right.
In the JT process, the gas is just flowing through a fixed obstacle. But there's still work being done. The high-pressure gas behind is doing work pushing the volume forward.
P1 times V1.
And work is being done on the gas as it exits at the lower pressure, P2, V2. So because the whole thing is thermally isolated and you account for this internal pressure volume work, the strict conservation law that applies here is that the enthalpy H must stay constant.
Okay, can you remind us what enthalpy is in simple terms?
Enthalpy H is basically the total energy content of a fluid that's flowing. It's the internal energy of the gas, U, plus what we call the flow energy, which is the pressure times the volume, PV. So saying H is constant just means the total energy flowing through that throttle is fixed.
Okay, here's where it gets really interesting for me. If the total energy content is constant, why does the temperature change at all? This feels like the core aha moment of the JT effect.
It is the aha moment. And the answer is, if the gas were truly ideal, if the atoms were just simple non-interacting points, the temperature wouldn't change.
It would stay constant.
It would stay constant. Because for an ideal gas, enthalpy only depends on temperature.
Right.
But we're not dealing with an ideal gas. We're dealing with a real gas.
And the difference is all about the stickiness of the atoms, right?
Exactly. In a real gas, the atoms or molecules, they're not just points, they have volume. And crucially for cooling, they attract each other through these weak intermolecular forces. We call them van der Waals forces.
So there's this subtle internal potential energy in the gas.
There is. So think about what happens when this real gas expands through the throttle. The particles are suddenly much, much further apart.
Okay.
To get further apart, they have to overcome that mutual attractive force. They have to do internal work against their own stickiness.
And where does the energy for that internal work come from?
It has to come from the only energy source available to them, their own kinetic energy.
The energy of their movement.
Yes. They convert kinetic energy into potential energy, which gets stored in their separation. And since the average kinetic energy of the particles is the definition of the temperature of the gas,
The particles slow down. The temperature drops.
the temperature drops. The gas cools itself upon expansion because the atoms have to spend their own energy to break free from each other.
I never realized that. The simple fact that atoms are attracted to each other is the very mechanism that lets us cool them. That's profound.
It's the entire foundation of industrial cryogenics. But, and this is a huge, but the sources really emphasize, this cooling only works if those attractive forces are the dominant ones. There's a critical flip side. The gas can actually heat up instead of cooling down.
How is that possible? How can a gas get hotter when it expands?
If you put the gas under extremely high pressure or you get it to a very high temperature, the short-range repulsive forces between the atoms start to take over. When they get too close, they push each other away.
Right, they don't want to occupy the same space.
But if the atoms are already moving really fast or they're squeezed super close together, repulsion becomes the dominant force, not attraction.
And if repulsive forces are dominant, what happens during the expansion?
Well, now when the system expands, it's actually releasing that internal potential energy that was stored in the repulsion. The particles are basically helping push each other apart.
I see.
That released potential energy gets converted back into kinetic energy, particles speed up, and the gas warms up.
So we need a very clear dividing line between these two behaviors.
We do, and there is one. Every real gas has a critical property called its inversion temperature, TINV. Below this temperature, the gas cools down when you do a JT expansion.
Attractive forces win.
Attractive forces win. And above this temperature, the gas heats up. Repulsive forces win.
And this inversion temperature isn't just some academic concept. It is a massive practical problem for anyone doing cryogenic work.
It dictates the entire strategy. For example, the air we breathe, which is mostly nitrogen and oxygen, has a really high inversion temperature. It's about 760 Kelvin.
Which is, what, almost 500 degrees Celsius? Way above room temperature.
Far above room temperature, which means that air cools down easily when you use the JT effect, starting from normal conditions. No problem.
But the gases we really want for deep cryogenics, hydrogen, and especially helium, they present a huge obstacle.
They're the ultimate challenge. Their inversion temperatures are incredibly low. For hydrogen, it's only about 200 Kelvin. For helium, it's a frigid 40 Kelvin.
So wait, that means if you took a tank of helium at room temperature and just let it expand through a valve, it wouldn't get colder.
It would get hotter. It would warm up.
Wow. So to even begin to liquefy helium, you have to pre-cool it by more than 250 degrees Celsius just to get to the point where its own internal attractive forces can start to do the cooling work for you.
Exactly. And that realization leads us directly to the industrialization of cold.
So we have this subtle physical principle, the Joule-Thomson effect, which might drop a gas's temperature by, 10 or 20 degrees in a single go?
Something like that.
But for mass liquefaction, we need sustained industrial scale cooling. We need to go way beyond what one little throttle can do.
And that's where the engineering really meets the physics, specifically in the Linde process.
This is the industrial standard.
It's the standard, yeah. It's used in all these massive air separation plants to produce liquid nitrogen, liquid oxygen, argon by the ton.
The genius of the Linde process, as our sources describe it, is that it combines the JT effect with one absolutely crucial piece of technology, The counterflow heat exchanger.
That component, you often see it as a G in the diagrams, is the self-sustaining heart of the whole machine. That single 20-degree cooling step isn't enough on its own. You need to feed that initial cooling back into the system to accelerate the effect, cycle after cycle.
A feedback loop.
A thermal feedback loop until the gas finally drops below its boiling point.
Okay, let's trace the full cycle here to see how this self-refrigeration works. We have to start with the mechanical input, compression.
Right. Air is compressed to a really high pressure, typically 200 bar, which is about 200 times atmospheric pressure. Again, this is the work input, and it makes the gas extremely hot.
So step 2 has to be getting rid of that initial heat.
Absolutely critical. The hot compressed gas has to be cooled back down to near room temperature, just using simple water or air coolers. If you skip this step, the gas gets to the throttle way too hot, and the whole thing fails.
Okay, so now we have high pressure gas at room temperature. It flows towards the throttle valve, but it has to pass through the long channels of this heat exchanger first.
Right. And then at the throttle, the JT expansion happens. Pressure drops from 200 bar all the way down to 1 bar. And the real gas cools itself, let's say by 15 or 20 degrees, because of those molecular forces we just talked about.
Oh.
But, and this is important, the gas is not liquid yet.
It's just colder. And here is the trick in action. You don't just vent that cold gas.
No, you recycle it. This is the critical self-sustaining loop. That cold, low-pressure gas that just expanded is routed backwards through the heat exchanger. It flows along the outer jacket.
And it chills the incoming high-pressure gas that's flowing towards the valve.
Exactly. So the next batch of high-pressure gas that gets to the throttle valve is already colder than room temperature to begin with.
I see. And because it started colder, it gets even colder after it expands.
Precisely. It was pre-cooled by the cold exhaust from the last cycle. This process enters a loop of what we call runaway cooling. The thermal feedback makes the system colder and colder with each pass, until the temperature finally drops below the boiling point of air.
And then liquid air just starts to drip out into a collector.
That's the product.
That's just phenomenal engineering. It's such an elegant way to multiply a very subtle physical effect into an industrial powerhouse.
And we can actually visualize this really clearly using what's called a TS diagram, a temperature entropy graph. It's how engineers track the whole process.
And the process happens between two specific pressure lines, or isobars, the 200-bar line and the 1-bar line.
Exactly. And the expansion in the valve itself is what we call an Eisenthal, a line of constant H. We don't need to get into the weeds with the thermodynamics, but what you see is that the countercurrent principle lets the system effectively slide down that 200-bar line, getting colder and colder.
Until it hits the target zone.
The target zone, which on the diagram is called the wet steam area. It's this characteristic bell curve. And once the state of the gas enters that region, thermodynamics says it has to separate into two phases, liquid and vapor. And that's where you collect your liquid product.
Okay, so let's go back to the ultimate challenge we talked about before, liquefying helium. The normal Lindo process just fails completely if you start at room temperature.
You always have to remember the 40 Kelvin inversion temperature. If you want to get to helium's boiling point, which is 4.2 Kelvin, you need a pretty serious multi-stage cooling process just to get past 40 Kelvin so the JT effect can even start helping you.
What are those stages?
Well, stage 1 is pre-cooling with something cheaper and easier to get, usually liquid nitrogen.
Which boils at 77 Kelvin.
Right, so that gets you a long way down from room temperature, but you're still well above that 40 Kelvin hurdle for helium.
So there's a huge gap there between 77K and 40K. We need another more powerful cooling mechanism to bridge that gap.
And this is where we bring in special machines called expansion engines, or sometimes heat engines. Now, unlike the JT expansion, where the gas is doing internal work against its own forces,
You make it do external work.
you force the gas to do external mechanical work, you make it push a piston or spin a turbine.
So you are physically pulling energy out of the helium gas stream.
Exactly. And the law of conservation of energy says that if you extract mechanical work from the gas, its internal energy, and therefore its temperature, has to drop a lot. This mechanical expansion is far more effective at cooling in this temperature range than the JT effect is.
And that's what gets you below 40 Kelvin.
That's what gets you into the JT cooling regime for helium. And only then, once the gas is finally below its inversion temperature, can you use the Joule-Thomson effect as the final step to reach 4.2 Kelvin and get your liquid helium.
It's an incredibly complex, staged, and expensive process just to get 4 degrees above absolute zero. So we've established how we get down to 4.2 Kelvin, but the reason we go through all that trouble is because of the truly revolutionary physics that starts to happen when we dip below the boiling point of liquid nitrogen at 77 K.
And that transition from nitrogen temperatures to helium temperatures, it comes with a very real price tag. It's important to remember the cost reality check.
Right.
Liquid nitrogen is common, it's cheap, less than €1 a liter. But the moment your experiment needs liquid helium, the cost can jump by a factor of 10 or even more.
So any research that relies on it is inherently expensive.
Expensive and complex to maintain, yes.
But that cost is justified by things like superconductivity. Can you explain the essence of this? Because it really challenges our everyday understanding of electricity.
Superconductivity is the complete, and I mean absolute, loss of all electrical resistance.
Zero resistance.
Zero. When you cool certain materials, metals like lead or niobium or certain ceramics, below their own specific critical temperature, their electrons just stop scattering. They start flowing in perfect unison.
So what does zero resistance mean in practice?
It means unbelievable efficiency. If you induce an electric current in a closed loop of superconducting wire, that current will flow, in theory, forever, without any energy loss.
Wow.
This is absolutely essential for building incredibly powerful and stable electromagnets. You think about the giant magnets in an MRI machine or the miles and miles of magnets in the particle accelerators at CERN. They need huge, stable magnetic field without generating massive amounts of heat from resistance.
It's a game changer for anything involving magnets or power transmission, but the need for that extreme cooling is still the big limitation.
It's the bottleneck. We're always hunting for so-called high-temperature superconductors, materials that can do this using cheap liquid nitrogen at 77 K instead of expensive liquid helium at 4.2 K.
Okay, now let's go even deeper, to the truly bizarre world of superfluidity. This happens specifically with helium-4. How do physicists even get to this state?
You start with liquid helium at its normal boiling point, 4.2 K, and then you just continuously pump away the helium vapor that's sitting above the liquid.
That reduces the pressure, which should lower the boiling point.
Exactly. And as you pump, the temperature drops until you hit a very precise point.
A magic point.
You could call it that.
Yeah.
At exactly 2.17 Kelvin. It's known as the lambda point because a graph of its specific heat looks like the Greek letter lambda. At that point, helium-4 undergoes a phase transition.
Not from liquid to solid.
No, from one kind of liquid to a completely different kind of liquid. It goes from a normal viscous liquid, which we call helium the first, to a quantum fluid, called helium the second, the superfluid state.
And at that point, the quantum mechanics of the atoms just takes over completely.
Completely. The liquid basically stops behaving like a classical liquid at all.
So what are some of these unbelievable properties?
Well, the first and most famous one is zero viscosity. It has no internal friction. It flows completely freely. If you were to stir it in a cup, it would just keep swirling forever.
And then there's the famous creeping phenomenon.
This one just defies all intuition. Superfluid helium will spontaneously form an incredibly thin film, just a few hundred atoms thick, on any surface it touches. And this film will literally crawl up and over the walls of its container.
It climbs out.
It climbs out, drips down the other side until the liquid level inside and outside the container is the same. It seems to just ignore gravity because there's zero friction to stop it.
So you can't really keep it in an open container.
You can't. It will creep out and evaporate away, and on top of that, it has the fountain effect. If you shine a light on a fine capillary tube that's submerged in the superfluid, the tiny bit of heat creates a pressure gradient that causes the liquid to shoot out of the tube like a miniature geyser.
Driven just by heat.
Just by thermal energy. And finally, its capacity for heat transport is just off the charts.
Better than copper.
Millions of times more effective than copper. If you put a small heater in one part of the superfluid, you can't even measure a temperature difference across the liquid. The heat propagates as a wave, a pulse of temperature change we call second sound. These properties really confirm that below that lambda point, you're not in the world of classical mechanics anymore. You are in a macroscopic quantum world.
2 Kelvin is incredibly cold. But for the most advanced quantum computing and physics research, scientists need to smash through the 1 Kelvin barrier and get down into the milli and even microkelvin range.
Right.
And to do that, we have to abandon the idea of phase changes entirely.
We do, because we hit the limit of evaporation. Around 1 Kelvin, the vapor pressure of the helium becomes so vanishingly small that there just aren't enough gas atoms left above the liquid to pump away. The technique becomes useless for getting any colder.
So we need new methods.
We need entirely new quantum mechanical methods that let us manipulate the internal energy states of the material itself.
And the first major technique for crossing that millikelvin barrier is called adiabatic demagnetization.
This method relies on manipulating the chaos or the entropy of the magnetic moments inside a material, usually a special kind of paramagnetic salt. We basically treat the tiny electron magnets inside that salt as if they were a kind of magnetic gas.
And the process has two very distinct steps. The first is about creating order, isothermal magnetization.
Exactly. You place your salt sample inside a very powerful superconducting electromagnet and you turn it on, all while keeping the temperature constant. The magnetic field forces all those little electron magnetic moments to align themselves with the field.
Which creates a very highly ordered system, low entropy.
A huge decrease in the system's internal chaos, its entropy. And as we know from thermodynamics, when you decrease entropy, you create order, and that generates heat.
So you have to get rid of that heat.
You do. That heat of magnetization has to be immediately carried away by the surrounding liquid helium bath. So at the end of this step, you have a very cold salt sample that is highly ordered, with extremely low magnetic entropy.
Okay, now for the cooling part. Adiabatic demagnetization.
Now, you thermally isolate the salt from its cold bath. You cut it off. Then you slowly turn the strong magnetic field off.
And what happens?
Well, the aligned magnetic moments suddenly want to go back to their natural state of chaos. They want to randomize themselves and maximize their entropy.
And they need energy to do that, to get all jumbled up again.
Precisely. The energy required for this disorder heat has to be taken from the only source available to them now that they're isolated.
The internal energy of the salt's own crystal lattice, the vibrations of the atoms.
Exactly. The electron spins literally steal the energy from the lattice vibrations, which causes the salt's internal energy to plummet. The temperature drops drastically, and this technique can reliably get you down to just a few millikelvin.
It's like an energetic sleight of hand. You use magnetism to organize the spins, and then you let their disorganization siphon off the thermal energy of the solid itself.
And the underlying physics is really captured beautifully if you look at it from an energy level view using the Zeeman effect. The magnetic field actually splits the energy levels that are available to the particles.
So in the high field step, the isothermal magnetization, the energy levels are spread far apart.
Very far apart. And because the system is cold, almost all the particles fall down into the lowest available energy level, aligning their spins with the field. That's our high-order, low-entropy state.
Then when you turn the field off, the adiabatic part, the energy levels collapse. They move much closer together.
Right. And because the process is adiabatic, meaning no heat gets in or out, the total entropy of that spin system has to stay constant. This is the key. You have the same distribution of particles, the same relative population numbers across the energy levels.
But the energy levels themselves, the rungs of the ladder, are much closer together now.
They're all compressed. And thermodynamics tells us that that specific population distribution, when it's sitting on those compressed energy levels, corresponds to a much, much lower overall temperature, T2. We've tricked the system into cooling itself by changing its internal energy structure.
And if a few millikelvin isn't cold enough, you have to go even deeper, pushing to microkelvin.
To get into the microkelvin range, you apply the exact same technique, adiabatic demagnetization, but you do it to the nuclear spins of the atoms instead of the electron spins. It's called nuclear demagnetization.
Why do you have to switch to the nucleus?
Because we're hunting for smaller and smaller enemy targets. An atomic nucleus has a magnetic moment that is thousands of times smaller than an electron's.
So the interactions between them are much weaker.
Much, much weaker. And because those internal interactions are weaker, the internal temperatures that can be achieved, temperature where the nuclear system itself would become magnetically ordered, are significantly lower.
But this sounds like a staged process. You must have to start incredibly cold to even begin.
Oh, absolutely. To get any meaningful alignment of the nuclear spins, you have to start the process already deep in the cold, typically around 0.01 Kelvin.
Which you get to using the electronic demagnetization we just discussed.
Right, it's a prerequisite. But once you start, nuclear demagnetization can achieve the lowest table temperatures humans have ever made, down to about 10 to 6 Kelvin, 1/millionth of a degree above absolute zero.
That is just the edge of thermal existence. But that magnetic process, it's a batch process, right? It cools down once, and then it slowly warms back up. How do researchers keep these temperatures stable for days or weeks for an experiment?
That brings us to the modern workhorse of quantum physics, the dilution refrigerator. or dilution cryostat. This machine provides continuous, stable cooling down into the millikelvin range.
And it uses this really exotic mixture of helium isotopes, helium-3 and helium-4.
It does. The physics relies on the bizarre phase properties of this mixture. If you cool it below about zero point 0.8 Kelvin, the mixture spontaneously separates into two phases, kind of like oil and water, but driven by quantum mechanics.
What are the two phases?
You get a layer of almost pure, concentrated helium-3 floating on top, and underneath it you get a phase that's mostly helium-4, but with a small, dilute concentration of helium-3 dissolved into it.
And how does that separation create continuous cooling?
This is the genius of it. The machine is designed to continuously pump helium-3 atoms out of that lower dilute phase. This creates a concentration gradient. So to replace the atoms that were just pumped out, new helium-3 atoms from the upper concentrated phase have to constantly evaporate or dissolve across the boundary into the lower phase.
So the He3 atoms are moving from their concentrated liquid state into this dilute liquid state.
And that migration is the cooling mechanism. Because of quantum statistical mechanics, a He3 atom dissolved in He4 has a much higher kinetic energy and, critically, a much higher entropy than an atom in the pure concentrated phase.
So moving from the concentrated phase to the dilute phase is like moving from a low entropy state to a high entropy state.
It is. And that process requires an input of energy, just like boiling water requires heat. The process of dilution has to pull that required heat energy from its immediate surroundings, which is your experimental stage.
So by constantly driving this phase migration, this evaporation from one liquid phase to another, you're forcing the system to continuously consume heat.
Precisely. And this ingenious sustained phase change allows for reliable, continuous operation down to about 10 millikelvin, which makes the dilution refrigerator absolutely indispensable for stabilizing quantum chips, detectors, and all the circuits used in modern physics research.
What an extraordinary deep dive this has been. I mean, we've moved from the simple mechanical compression in your kitchen refrigerator, which relies on the heat of vaporization,
Right.
through the industrial scale of the Lin process, which multiplies those subtle molecular forces in the Joule-Thomson effect, all the way to manipulating quantum spin states and isotopic phase separation to reach temperatures where classical physics just completely breaks down.
It really does highlight how a mastery of thermodynamics lets us harness these fundamental forces to engineer our energy landscape. It doesn't matter if we're dealing with the slight stickiness between gas atoms that allows JT cooling, or leveraging entropy and magnetic order to siphon away heat. We're just constantly finding new ways to control matter near absolute zero.
We've really seen the physical limits get pushed to the absolute extreme edge of what's currently possible here on Earth. And it shows that cold isn't just the absence of energy, it's a unique environment where the universe reveals its strangest secrets.
Which I think raises an important final question for you to think about. We've mastered temperatures down to the microkelvin range, relying on entropy, magnetism, and quantum phase separation. But what fundamental physical limits remain to be broken by mastering temperature control? Given that the third law of thermodynamics states that absolute zero is unattainable, will future advancements in quantum manipulation allow us to functionally reach that point in any meaningful way? Or are we forever destined to just approach it but never actually touch it? Something to ponder until our next deep dives.